An understanding of the principles of magnetism is basic to the understanding of electrical and electronic devices.
Electrical control devices, such as solenoids, relays, and transformers, rely on magnetism for their operation. Electrical voltage is produced by generators using magnetism, and machinery is driven by electrical motors that use magnetism to develop their rotational power.
There are only three substances that form natural magnets. They are iron, nickel, and cobalt.
The ability of these materials to become magnetized is based upon their electron spin patterns. When most atoms combine to form molecules, they arrange themselves so that the magnetic effect of their electron spin pattern is canceled. This does not happen in the case of iron, nickel, and cobalt. These atoms produce small areas called magnetic domains, which act like small permanent magnets. In order to make this material into a magnet, these domains must be organized in an orderly pattern. This is done by passing a strong magnetic field across the material. A magnet is surrounded by imaginary lines of force that form a three-dimensional pattern called a magnetic field.
The effect of this force field, or flux lines, can be observed.
If you place a sheet of transparency over a bar magnet and sprinkle iron filings on the film, the iron filings will settle into a pattern caused by the invisible three-dimensional magnetic field that surrounds the magnet. The magnetic field is shown more clearly in this diagram. The lines around the magnet represent the magnetic flux lines.
Scientists have discovered 6 basic rules for the behavior of magnetic lines of force. Number 1, magnetic lines of force have both polarity and direction.
The ends of the magnet are the magnetic poles, where most of the magnetic force is concentrated. They are designated N for north and S for south. By definition, the lines of force always leave the north pole and enter the south pole. Arrowheads are often added to the diagram of the magnetic field of a magnet to indicate magnetic field direction.
Number 2, lines of magnetic force always form complete loops.
The flux lines around a magnet are considered to continue through the magnet. Outside the magnet, the lines of force go from the North Pole to the South Pole, but inside, the magnetic lines of force go from the South Pole to the North Pole, forming complete loops.
Number 3, magnetic lines of force will never touch each other or cross.
If the lines of force are polarized in the same direction, they repel each other, keeping them separate from one another.
Number 4, lines of magnetic force always tend to form the smallest possible loop.
They act like stretched rubber bands, trying to contract right down to the surface of the magnet. It is this balance of the forces of contraction and repulsion that results in the field patterns.
Number 5, there is no known insulator for magnetic lines of force.
They will pass through all materials, but they will go through some materials more easily than others.
And number 6, magnetic lines of force always enter and leave a magnet perpendicular to its surface.
Most of the magnetic flux enters and leaves at the magnetic poles, but some also leave at right angles to each side. The symbol used to represent magnetic flux is the Greek letter phi.
The standard unit of measurement of the number of magnetic lines of force, or magnetic flux, is the Weber, abbreviated WB.
1 Weber is equal to 10 to the 8th power, or 100 million lines of force. Because the amount of magnetic lines of force may vary with different sizes and shapes of magnets, it is necessary to know both the number of lines of force and the size of the area through which they pass. The measurement of the magnetic field strength is known as the flux density.
The standard unit of measurement is the Tesla and is identified by the capital letter B.
A Tesla is equal to a Weber per square meter, that is, 10 magnetic lines of force passing through an area 1 meter by 1 meter. This relationship between the Weber and the Tesla can be put in the form of a single formula. Tesla B equals phi over m, where phi equals number of lines of force in Webers and m equals the cross-sectional area of the magnetic path in square meters.
Now, let's see how magnetic poles react to each other.
Hang a bar magnet by a string fastened to the center so the magnet is free to rotate. Next, hold a second magnet near the first so that the north poles are facing each other. Because of the force of repulsion, the magnet on the string will rotate away from the second magnet. This is also true when the south poles are brought together. But if a south pole is brought near to a north pole, a force of attraction exists. The magnets will come together.
These simple tests demonstrate the two basic laws of magnetism. Like poles repel and unlike poles attract.
Let's analyze the flux patterns of the two magnets with like poles together. Since the lines of force cannot cross each other, they therefore turn aside and travel in the same direction between the pole faces of the two magnets. The magnets mutually repel each other. Look at the flux pattern of the two magnets with unlike poles together. Remember, lines of force flow from north to south and act like stretched rubber bands. Since the lines of force are stretched across both magnets, they tend to resist this stretching effect and to draw both magnets together.
Although magnetic lines of force pass through all substances under normal conditions, there is an opposition to their passage.
This opposition that a substance offers to magnetic flux is known as reluctance. The ability of a material to permit lines of force to pass through it is called its permeability. Flux lines pass more easily through material of high permeability, such as iron, than they do through air. Magnetic materials are ones that are strongly attracted by a magnet. They are classified as ferromagnetic and include nickel, iron, cobalt, and alloys made with these metals. Paramagnetic materials are metals that can be magnetized but not as easily as ferromagnetic. Some examples of paramagnetic materials are liquid oxygen, titanium, and platinum. Diamagnetic materials are materials that are not attracted by a magnet. These materials are liquid hydrogen, pure water, silver, and copper.
Now, let's see why magnets attract objects made of magnetic or highly permeable materials.
Since such magnetic materials provide an easier path than air for the magnetic lines of force, some of them are diverted to the magnetic object, causing the field to be distorted. Remember that lines of force tend to contract. Therefore, as they pass through the magnetic object, they pull it toward the magnet. The lines of force passing through the magnetic material has made it into another magnet. This process of being magnetized is known as magnetic induction.